Good afternoon, everyone. Thank you so much for being here. I know it's been a long couple of days, and I really appreciate that you've made it to my talk. I hope you've had fun, and I definitely hope that you will enjoy this talk. So, as Jeremy mentioned, thanks for the wonderful introduction, Jeremy, and thanks to Formulated By for inviting me to speak. My name is Anabetsy Rivero. I'm the co-founder and CEO of Metastatic AI. We are a Miami-based artificial intelligence company for cancer diagnosis. This is not a sales pitch for my company, so I will be speaking very little about my company, and if you're interested in hearing more about it, we can talk about it later. You can follow me on Twitter or follow my company on Twitter. So my path to data science has been rather strange. I started as a biochemist, a molecular biologist at University of Miami, doing cancer research and genomics research and protein-protein interactions, you name it. My research career started at Harvard Medical School and University of Miami. And then something wonderful happened. I was doing oncology and genomics research, and I realized that a lot of my colleagues were doing very advanced analysis, and they were writing Python scripts and R scripts, and I had no idea what that was. I was almost typing with 2 fingers at the time. And I decided to learn how to code, taught myself how to code, and got into a master's in computer science, where I specialized in artificial intelligence and data mining. And then went on to challenge myself a little bit more, wrote my own deep learning library, from which I derived all the application for my platform, for my company. You know, a lot of people think of this, when they think of AI, they think of the movies and the computers that are coming out to kill us and eat us alive, right? and the games and all of these things is a big PR effort, but even though it's very interesting, I think what's more interesting is the underlying mechanisms that are powering all these different algorithms and all these different applications that we see. So in reality, what we have in AI, in deep learning, it's of far more value than what you see in this slide. And it's more like weather prediction. I've seen some people are using neural networks, for example, for weather prediction and hurricanes. I believe actually that IBM Watson is actually doing some of the weather predictions these days. Also, one of the most important applications is quantitative trading. Wall Street, as many of you know, is not the same anymore. It's mostly run by AI machines, and then they have the cool bell to kind of ring and make it all fancy. One of my favorite things, though, is the self-driving cars, and last but not least, conversational AIs like the Amazon Echo and Google Home, etc. But what is deep learning? So initially, we had the field of artificial intelligence, which is not new. Many of you know there's been a lot of research efforts done by MIT and Stanford and other universities since early on. And they had a bunch of different algorithms about path searching and a bunch of different things about robotic navigation, which are not the most interesting, in my opinion. And then we kind of went more into machine learning. And so machine learning is special, at least to me, because then we have algorithms that are capable of self-adapting and learning in a similar way than a human being. That's very important, because then that eliminated our need to explicitly program with all these instructions, if-then statements. And now we have computers that are capable of learning a little bit. My specialty is neural networks. That's what I love the most in this world. My life changed the day I learned about neural networks. Because, from a biology background, coming from this biology background, I realized the similarities. They're quite loosely modeled after the human brain, which is really the most beautiful, perfect machine that you will ever see. We don't even understand all about the human brain, but recently now we've developed even more robust algorithms that are kind of fall under the category of deep learning, where we're not only able to model the human brain or certain regions of the human brain, but we're working towards more specialized capabilities and more sophisticated capabilities by using deep learning and trying to kind of simulate what the human brain is capable of doing with computer vision, for example, As many as you know, the visual cortex of the human brain is amazing. Our field of view, this is a very sophisticated sensorial system, and deep learning simulates that in a rather sophisticated way, in my opinion. So what are neural networks? As I said, they're loosely modeled after the human brain, kind of simplified, but you have the concept of neurons. In this case, each of these circles is a neuron. Then all of these connections kind of simulate the synapses between these neurons that allow us to make connections and pass signals in the brain. It's neurotransmitter signals that go from one neuron to the other and allow us to make decisions, allow us to blink, allow us to feel hunger. And then you actually have layers of these neurons that actually form different subregions in the brain that allow us to perform very specialized calculations, or such as human vision, for example. Now, one of the most important findings in neural networks theory is that some experts found pretty early on that neural networks are like work as a universal approximator. What neural networks do is that based on inputs, they are capable of approximating any function, assuming you have sufficient data and assuming you have a sufficiently large number of neurons in this middle layer, which we call the hidden layer, and you'll see a lot more of that. But in reality, you don't always have an unlimited amount of data or a large amount of data, and you also don't have an unlimited number of features to be able to approximate any function. So then we kind of have to move into deep learning rather than this simplified model. Neural networks, of course, and deep learning can also be optimized by different methods that I'm sure many of you are familiar with. The purpose of this talk is not to give you a whole lecture on all the different methods, but rather bring us together to be on the same page and then talk about the applications in medicine and so on. As many of you know, these networks, at the end, when you actually produce an output or a decision, for example, in medical diagnosis, you decide, or the network decides if a person has cancer or not. In order to make that decision, this happens with equations that are called activation functions. Fancy term for rather simple equations that allow us to make these decisions and really beautifully model the data and actually find some use out of these equations. And in a way, it cannot really simulate the brain, because if you think about it, the brain, when you actually encounter a signal, say you're burning, very rapidly this signal travels to your brain, and your brain determines, I'm burning, I'm gonna remove my finger from the stove, right? That is, the neuron actually made a decision to fire. It was really a 1, not a 0. If it was a 0, then you keep the finger on the stove and you get burned, which, by the way, there's a disease in which that happens. But in this case, the neuron decides if it's going to fire or not, and of course you can determine if it fires, for example, you get a 1 and you get a diagnosis of cancer, and if you get a 0, for example, you don't have cancer. And this is a very simplistic view of how these things work. Lastly, there are many different flavors of neural networks. There's the 3-layer, the multi-layer perceptron, which is really the simplest one, from which a lot of research kind of came from. But then you have convolutional neural networks, you have recurrent neural networks, and those are some of the most powerful and widely used this year at least. This is a somewhat simplified neuron in the context of neural networks. And what this means, if you see there, you have your input signals, that's your input vector, right? And where you're getting your data coming in. And this data is propagating in a feed-forward manner where you're doing all these calculations, you're adding those weights, and you're adding your bias, which is actually very important. And then you're actually going to do these calculations, and then you produce an output. This output is whether, like I said, whether the neuron fires or not, whether you have cancer or not, or whether you have a cat or a dog, and so on. I don't want to bore you with the math. I love math, and I would love to talk more about it, but I don't want to put you to sleep. So I thought this was kind of fun. For those who might find neural networks a little confusing. So there's several types of machine learning. And so we've been discussing this since yesterday. We have supervised learning, unsupervised learning, and somewhere in between, you kind of have a mixture of semi-supervised learning. And then we have the very famous reinforcement learning that we were discussing yesterday. SK did a wonderful job, actually, of talking about reinforcement learning in self-driving technologies and things like that, where you have an agent and you're actually giving a reward or a penalty if they make a mistake. And I have to say, I mostly specialize in supervised learning. I really like it, and fortunately, a lot of the data that I work with, it's already labeled for me, conveniently, right? So that's kind of my favorite in this case, if you want to know about my biases. As I mentioned, we have several types of neural networks. You have the traditional, vanilla, artificial neural networks, which have fully connected layers, and I'll go more in depth into what that means. And they can be shallow, meaning 3 layers, or they can be deep, and you can have many layers of those. You also have the recurrent neural networks. I will go into the applications of each of them, but the most important feature of recurrent neural networks is that they have feedback loops that can kind of feed back into themselves. And the most important thing is that they can actually be used for temporal information, time series data, forecasting, lots of very interesting applications, but they more often than not have to do with time. And lastly, we have the convolutional neural networks, which I'm sure everybody here probably knows about. They're not necessarily fully connected. You usually have, what I'll show you later, you have convolutional layers, then you have some pooling layers, and you kind of keep mixing them. And then at the end, you usually have a fully connected network to actually make that decision of whether the neuron will fire or not. This is an example. Pretty picture that we put together to kind of show people what we do at my company, and it's just a very pretty representation of it. As you can imagine, it took a long time to get all those lines and all those neurons together. But this is what I'm saying. Anything that has more than 3 layers technically is a deep neural network, even though that's not very deep per se. And as you can see, you have your input layer, you have several hidden layers. This can be 1,000 or 100 or whatever. And then you have your output layer where the decision is made. These are a bit more simplistic, and I got these from Google Images, in case you're curious. This is more of the image of recurrent neural network, a very simple image of recurrent neural network. And these are the feedback loops that I was talking about, where you actually take into account all this temporal information to make a decision. Lastly, convolutional neural networks are probably the fanciest of them all. And you basically have an image. It's really good for 2D data, for example, like images and things like that, for self-driving cars, where you have this grid of data in 2 dimensions, and then you actually play with those dimensions to basically do the convolution first, and then subsampling to basically be able to detect objects, detect edges, and a bunch of different things, and eventually you can do classification as well. Now, these are some of the general uses of deep learning. This is by no means exhaustive, but just to give you an idea, stock market forecasting, word prediction when you're writing down things on Google, for example. Translation is one of the most important things, as they all kind of have a temporal component of what you're doing now versus what you're doing next. And speech recognition. In the context of convolutional neural nets, gets a little fancy. You have the object recognition, image classification. Of course, these things can get very sophisticated. You have edge detection. For example, you have one image. I remember, I think SK mentioned yesterday, when you have an image, if you think you're going to blur the image and send it to some significant other, and then no, machines are not going to see it, you're wrong, because machines are going to see it. There are methods of removing all that blur and detecting the edges and doing all this fancy stuff, and you can get your image back. So be careful with what you post and send. And of course, you have recommender systems. Those are one of my favorite. And you don't need a convolutional neural network necessarily for that. You can do it with by many different methods. I believe I may have mixed them. But anyway, under deep learning, basically, you can have convolutional neural networks, recommender systems, natural language processing. Some people are using deep learning actually for fraud detection, as well as anomaly detection in networks and for cybersecurity purposes. Now, what that talk really is about It's about medicine. What is machine learning and AI and deep learning doing in medicine? I didn't want to start you right in medicine because I wanted to bring everybody up to the same level in a way so that we can be on the same page. So some of the applications in medicine you may have come across or not. Some of the times, for example, if you come from a different country, like I came from Cuba 10 years ago, I didn't speak English, and I now speak a bit. But back then, if I had gone to the doctor, I wouldn't have understood a single word they said to me. And they didn't have these technologies, but imagine if you go to the doctor and you're able to have a technology that is capable of translating what the doctor is telling you, and is capable of translating your language so that the doctor can understand you better. That exists now. You have, and I will show you some of my colleagues that are doing very interesting things in these areas. You can have a virtual nurse, for example, for the elderly. There's a huge problem we're having in this country where the elderly, they don't have money, and they're basically displaced and sent to these nursing homes where sometimes they treat them poorly and all these things. And now we're able to produce more value-based care to the elderly based on these virtual nurses and caregivers. Some other interesting predictions that you can make, for example, is predicting whether a person will be rehospitalized. Readmission rates, that's a huge problem that if any of you can solve, that is gold for the healthcare system. Hospital-acquired infections, huge deal. A lot of people go into the hospital for one little thing, and then they come out, and well, sometimes they don't come out. And if they come out, then they come back in and get an infection, and all of these things cannot lead to death when they're poorly implemented. But with the help of AI and a good implementation, they can be solved or at least improved. Now, my specialty is more in the diagnosis, prognosis, genomics aspect of it, and I'll show you some examples too. In diagnosis, of course, you can take images, biopsies, and you can use natural language processing to read through unstructured data and things like that. Prognosis is pretty easy, depending on the indicators that you have. Assuming you have the right data, it's pretty easy. Genomics and personalized medicine, on the other hand, are not so easy. You have a problem with an extreme number of dimensions that you have to somehow bring down, and there are many techniques to reduce your dimensionality in this problem, but it's still extremely complex. And unfortunately, the biggest problem we have is the data scientists are usually not genomics experts, and genomics experts are not usually data scientists. So we have a huge divide. If you sit them at the table, they're speaking two different conversations, which is something I'm trying to see if I can convince more people to kind of do both, right? And actually, one of the hottest topics these days is drug discovery, AI-assisted drug discovery and design. And I'll show you even one of the companies that started as an AI genomics company turned into a drug discovery and design company because the drug companies were like chasing after them. Hey, can you design drugs for me? And of course, this is very lucrative, and you don't have a lot of the other problems in going to the hospital and so on. So they ended up doing drug discovery and design for big pharma. And last but not least, clinical trial matching. This is a huge problem because companies are spending millions and millions for each clinical trial, and they don't know which patients to find. If a clinical trial fails, they spend millions and millions and haven't even solved the problem. And there's immense applications of AI in these fields. So to give you some examples, like I said, I didn't want this presentation to be a sales pitch about my company, so I'm not going to show you what we do. I'm going to show you rather what some of my colleagues here in Miami and somewhere else are doing. These are two Miami-based companies. One of them, SpeechMed, is actually here at the CIC. She's a wonderful lady. And she actually realized that there was a need for this multi-language translation tool in real time for doctors and patients, which is why I actually get goosebumps when I say it. This is one of the most amazing ideas of someone that was using this in a different industry and brought it to healthcare, and they're doing amazing things to help these patients who don't speak English, for example. CareAngel, on the other hand, also a Miami-based company, really great guys, and I'm not getting paid to say any of these, by the way. They actually are the world's first AI-based virtual nurse assistant. Remember when I said that the elderly is struggling to get assistance and they don't have money and all of these problems that we're getting with our older generations? These guys are actually helping in this solve this problem basically by having these AI assistants that can help patients. And then if there's a problem or something, then they can send real-time alerts to physicians to take care of their patients. In the AI-based genomics and drug discovery, this is very interesting. Remember, I mentioned some of them started as genomics, and then they ended up going into big pharma. Okay, I'll hurry up. So Deep Genomics is a Canadian company. They started in genomics, turned into big pharma, looked them up, really, really smart guys. Deep Variant, very interesting. They've done a great PR campaign. They came out of Google, and all they're doing really is calling genetic variants from next generation sequencing data, but Google's PR efforts somehow have made it seem very different from what they really are doing. So be careful what you read and make sure that you read with critical thinking. This is super exciting for me. Arteri is the first FDA-approved AI-based system for healthcare. They're doing cardiovascular imaging. They got their FDA approval. They partnered with GE Healthcare to bring this to market. Amazing. Up until this point, I think they got the FDA approval last year, at the beginning of last year. First company to do this, amazing. I encourage you to look them up. And here we have more like the clinical trial thing, IBM Watson. I'm sure most of you know all of these systems. But before we leave, since I don't have a lot of time, I want to show you a little video, hopefully. Oh, it's taking a while. I don't know why it's not showing the video. How can I show the video? Anybody know? I'm trying to show this video, but it's not quite. It's not quite. Well, it's just redirected to.
Let me see if we do this.
I basically clicked.
You clicked from the.
Yeah, I clicked on the presentation, and this is what it brought me.
Is it there?
No, I clicked here, and then it takes me to Google. But for some reason, it's not doing it. What a shame. Is there any way that I can cast this?
I really don't know. Let me see. Carlos.
Oh, maybe drag over?
Drag over. See? Can you send this video today? It's not playing?
No, it's playing, but it's not playing there.
Exit full screen, drag it over. Exactly. Okay, so. Yeah, but how do we?
Oh, give me a second.
Just keep it.
Yeah. No.
Oops,
No, what are you doing? Okay. Sorry for the technical difficulties. Talk about technical people having technical difficulties. I promise I think you'll like this. I picked it for the last slide so that you can enjoy the beauty of AI in healthcare. I hope you enjoy it. Thank you very much. Oh, it's, sorry. Where is it?
Sorry, guys.
Sorry, more difficulties, of course. Now there's no image. Okay. Oh, thanks. Enjoy.
How are you feeling today?
Like roadkill.
I'm sorry to hear that. Would you like me to send a message to your team to see if there's anything they can do?
Yes.
I'm glad you were able to talk with your pharmacist and that they adjusted your medication. How are you feeling today?
Better. Thanks, Patsy.
It's a nice, sunny day out. Think you might go for a walk?
Sure.
Don't forget your medication and a bottle of water. Want me to set a reminder?
Good idea.
Can you hear me? Thank you so much. That's on. It's on. Thank you. Questions, concerns, suggestions?
Thanks. Hi, Anabetsy. I've seen you pitch your company, and I know you're very humble in not sharing with us about your company, but I would love for you to share a little bit about your company, because I know it has a very powerful mission.
Hello, thank you. Thank you for asking. Like I mentioned, I didn't want it to be a sales pitch. I didn't want to be, that person. I wanted to talk about what matters, the AI and so on, and the technology and the potential for it. So my company, to tell you more, it's called Metastatic AI. We're Miami-based. We are AI for cancer diagnosis. What we do currently is to diagnose breast cancer with over 99% accuracy in under 1 millisecond. And we're hoping to save patients and insurance companies money. We're hoping to do the clinical trials and get FDA approval this year as a medical device, and hopefully bring it to market and save lots of lives. Thank you. No more questions then? Did I do a good job or a terrible job? I'm not sure. Thanks, guys. I hope you enjoyed.